Have a copy of the notes? Your homework assignment's due on Tuesday. We'll talk about the handout problem a little bit today. And we've already done the nodal method so that you can do problem 42. We're going to be starting on something called the Hardy-Cross method today, and we'll continue it on Tuesday. It's a really important part of the course, and so we'll spend a lot of time on it. So let's discuss this problem from the homework assignment. You can solve this by applying the nodal method, and specifically, we had this formula presented before. And what we say is water flows from 1 towards 2. And remember, this is just a rearrangement of the energy equation where H means head, and that is the sum of the three head terms, which is the pressure head, velocity head, and elevation head. And we've got a reservoir connected to a pipe network, two reservoirs, and because we know the elevation of the water surface in the reservoir, that means that we know the head at A is 25 meters. We assume that there's no losses in the pipe between here and here. And we assume that the head at B is 20 meters. And so we can apply the nodal method to express the flow through pipe AC as a function of the characteristics of that pipe. And so in this equation, you say the head at 2 and the head at the 1. So you have to guess some flow direction. Let's say we guess that the water is going from C towards A, just as an initial guess. That means if the water is going from C towards A, that means that the head at C has to be greater than the head at A. That's what that would mean if the flow was going from C to A. And so we'd say that the head at 2 would be location C, is the, no, I've said that backwards. If head at C is greater than the head at A, then that would make location 1 C, because it's going to be the total amount of head then minus the losses through the pipe. And so the losses in the pipe are this term here, plus if there's a pump between it, and there's not. And so what you can do is you can write the unknown flow here in terms of the characteristics, and you also can write the same equation from here, but it's going to be related to a known amount. It's going to be related to the 20 meters here. That will be the head at the downstream junction, 25 meters at the junction at A. And then your second equation would be continuity relationship, and that is that the flow into this junction is going to be the given 0.2 cubic meters per second and has to equal the flow through the two pipes. So you assume a flow direction in each pipe just to begin. And you can draw a little arrow on the handout that I've given you if that helps you keep it straight. You assume some flow direction, and we know that ultimately the flow through AC and BC is going to equal 0.2 cubic meters per second. So that's the implication of continuity. And we know the head is given at A and B because of those reservoirs that are connected. And so we know how much head there is there. And we can calculate the head at C in terms of this unknown flow rate. And so the head at C just depends on how much water is flowing through pipe AC. And the head at C has to be the same whether you go from here towards there or from here towards there. The head is going to be equal once you get to the ending point. Head decreases in the direction of flow. So in your first thing where you assumed the flow direction, if you assume it goes from C towards A, that means that the head at C will be greater, because head decreases in the direction of flow or increases against the direction of flow. That's what that just says. And so you'll come up with two equations, two unknown kind of a thing. And when you go through and solve it, you get a solution that is the square root of a negative number, or you get a flow rate that's negative, that's an indication that the initial flow direction that you assumed is wrong. And so you have to assume a different flow direction in one of the pipes and try again. So I think that I maybe give the same kind of assistance and a little bit more detail on the handout itself on how to solve this problem. But the bottom line is it's just a nodal method because you're considering a junction where you know the flow rates have to balance. The flow in equals the flow out at C, at D, actually at all of the junctions. And once you know what the flow rates through the pipes are, then you can tell if water is flowing out from the reservoir to make up the balance. Because you'll find by balancing at junction C, you're going to find the flow through AC. And you're going to find the flow through BC. And then you can do a similar flow balance at junction D, and you'll find the flow rate here, AD, and the flow BD. But flow might also be coming into and out of the reservoir to make up any difference. Okay. All right. So you need to adjust the flow direction assumption if your answers for flow rate end up being imaginary or negative. That's enough of the nodal method for now. We're going to start on something called the loop method. Sometimes it's called the Hardy-Cross method. In honor of its inventor, this procedure was developed by someone who worked at the University of Illinois, and he was both a structural engineer and a water resources engineer, which is kind of an unusual combination now, but at the time he found that there were some relationships between numerical methods needed to solve indeterminate structural systems and indeterminate pipe networks like this. So consider a pipe network shown where you've got water coming in to an inlet and going out through a variety of outlets, but how much water is going through any one of these pipes, we don't necessarily know. There could be multiple flow paths between the inlet and the outlet. And so what the Hardy-Cross method allows us to do is move beyond the simple problems in the nodal method. In the nodal method, it's a relatively simple path from inlet to outlet. But in the loop method, the pipe networks are a lot more complex. The way that we implement this method is starting with a guess. And that's how a lot of our solutions are, is we estimate something and we iterate several times, and a solution eventually starts to converge. And so the iterations that we can do with this loop method can be automated with spreadsheets, which is good news because the hand calculations for them are a little bit tedious. We'll go through one set of hand calculations, just enough to get a feel for what the formulas are and how to apply them, and then what it'll really do is make you appreciate how Excel is able to expedite the process. So you can do this by hand or by spreadsheet, and you can also do it by computer. And it's this Hardy-Cross method that's built into water gems, and regardless of which friction loss approach you have it set at, whether you choose Manning or Hazen-Williams or Darcy-Weisbach, it's using the Hardy-Cross method for computations as it tells you what the flow rates through each pipe is. So that's the basis for all of the software we use for hydraulic design today. One of the things that we have to do is think about how much resistance the flow there is through each pipe. And so the variable R in the equation that's shown there is meant to represent the terms of the Darcy-Weisbach equation that aren't shown. Previously we've said that the Darcy-Weisbach equation says that head loss due to pipe friction is FLV squared divided by D2G. And so we can also express it FLQ squared divided by D2GA squared. And so in the Hardy-Cross method, one of the first things that we do is we look at a pipe and we want to find out how much resistance to flow there is through that pipe. And so we have all of these lumped together as R. And if you're using the Darcy-Weisbach equation, the exponent factor here, Q to the 2 power. If you're using the Hazen-Williams, then it's 1.85. But we'll use Darcy-Weisbach. And so that Q will be to the 2 power. And so one of our first steps will be to look at a system and identify the diameter of the pipe, and therefore the cross-sectional area, the length of the pipe. And now F, that's a little bit problematic though, right? Because remember, we don't know the roughness of the pipe until we know how much water is flowing through it. And so not only are we going to be guessing what the initial flow rate is, but we'll also have to come up with an initial guess of the pipe friction factor F. Yeah?
Why would it be R times
Q in?
Q to the N over A to the N?
Because A is a property of the pipe and not of the friction loss method that you're using. It's an interesting question. I think we won't use the Hazen-Williams equation when we apply Hardy-Cross, and so I guess what I really ought to just say is that it's always going to be 2. But if you were using the Hazen-Williams equation, area is still, if you want to find velocity, it's still Q divided by A. And so V squared, we do Q divided by A squared. So your point, you're asking, if we're going to do V to the 1.85, why wouldn't it be Q to the 1.85 and A to the 1.85? That's your question? I'll have to think about that and get back to you. I'm not sure. But the good news is that that issue won't affect us because we're going to use Darcy-Weisbach. Okay, so as I was mentioning, we're going to have to estimate initially both an F value and a Q value when we get started. And how can we start with an estimate of F? What's a good way for us to have something reasonable to begin with? Do we just pick a value in the middle of the Moody diagram?
Look at pipe material first.
Okay, pipe material will have something to do with it. The fully turbulent flow assumption will be a great way. And remember, in a previous lecture, what we said was that when you don't know any better, you can just find the F value by ignoring the Reynolds number, and you'll assume fully turbulent flow for that first F value. And it may turn out that the velocity through the pipe isn't fast enough to justify the fully turbulent flow assumption, but that's okay because the second time through the Hardy-Cross method, we'll use the Jane equation to calculate F, not the fully turbulent flow assumption. All right. So let's just an example of how to calculate R. If we do have a known flow rate of 400 liters per second, then that'll allow us to calculate the Reynolds number. We've got concrete pipe, which gives us an equivalent sand roughness of 1.6 millimeters. The pipe length that's known is 85 meters long. So the R value here we can calculate as FL divided by 2G A squared times D. For the flow rate of 400 liters per second, that's 0.4 cubic meters per second. For a diameter of 750 millimeters, that's 0.75 meters, which gives us an area is 0.4418 meters squared. All right, so R, where is going to depend on F. So if we were going to use the fully turbulent flow assumption, then we would just have remember how I told you can calculate the Jane equation in base 10 log or natural log. Natural log is how we usually do it, and that's when it's 1.325 in the numerator. Here, just in my notes, I've got it from back when I was working it with the base 10 formula for the Jane equation. It would look like for the fully turbulent flow assumption. So that works out to an F value of 0.0238. But we do know the flow rate, and we can calculate the velocity. So here the velocity is going to be Q divided by area. Works out to 0.905 meters per second. And so the Reynolds number can be calculated by V times D divided by the kinematic viscosity. That's 679,061. And so we can put that into the full Jane equation, 1.325, the logarithm of 1.6 millimeters divided by 3.7 times 750 millimeters plus 5.74 divided by the Reynolds number to the 0.9 power, 679,061. 0.9 power. So the question is, how different is it? That's squared. 0.0242. A little bit different. 10%. Maybe. Okay, so we'll use the actual F value. And the R that we end up with is going to be 0.024 times 85 meters divided by 2G and the area 0.4418 meters squared, and the diameter of the pipe 0.75 meters. So the R value is 0.7103, and the units of R are seconds squared divided by meters to the fifth. Oh, area squared, right. That makes more sense. So that's how the R is calculated. In the next example, I don't have you calculate the R because it's more about applying the formula. So the R's will just be given directly to get a feel for how the calculations proceed. But what we should think of is that if you have a longer pipe, you're going to have a larger R. Or if you have a large diameter pipe, you'll have a smaller R. All of the things, the trends we talked about last time with the nodal equation, when we were trying to compare, which of the pipes would have more flow, all of that still applies when we are applying the Hardy-Cross procedure. So here is the procedure. And the procedure is summarized on the last page of the notes that I've given you today. There's a little handout there that explains all of the steps to follow in applying the Hardy-Cross method. So if we look at this indeterminate system here, this example shows that there's 100 something. Maybe it's CFS, maybe it's cubic meters per second. It doesn't matter. There's 100 going in at that lower left corner. And then water is going to be flowing through two pipes. One has an R value of 6, the other has an R value of 5. So if you had to guess, which one of those do you think is going to have more flow? The pipe on the bottom, the horizontal pipe, or the vertical pipe? Of these two, the water is going to, some of it's going to go through this one, some of it's going to go through that one. Which is going to have more flow? So the horizontal one is going to have more flow because there's less resistance. The R value is lower, is conducive to more flow going through it. What you can see is there's two loops, and so we're going to have to label each of them. We'll call one of them loop 1, the other will be called loop 2. Here we're going to apply the Darcy-Weisbach equation, and so n is going to be 2 in our formula. The n value that we use, it'll come into play in this formula when we apply it. In step 3, by define a direction, what I mean is that we're going to assume clockwise is positive. So within each loop, we're going to make some guess about which way the flow is going. Let's see. Here is our system. There's 100 coming in, and there's that diagonal pipe there. 30 comes out, 50 comes out there, and 20 goes out here. Okay, so first of all, we're going to call the lower loop, loop 1. This we'll call loop 1. We'll call this one loop 2. And we'll have clockwise be positive. And how that comes into play is we're assuming that the water goes this way and this way to begin with, right? So this flow is going to be a positive flow. When we go through our numerical procedure, the vertical pipe, since it's in the same direction as that loop, you can see that the loop would say positive is up for that pipe. But for the horizontal pipe, that flow to the right is against the positive direction that's defined by this little clockwise is positive notation. Let's call this junction 1. We'll call this junction 2, this junction 3, and that will be junction 4. So the way that I'm going to refer to pipes is by their junction numbers. There's going to be pipe 1, 2. There will be pipe 2, 3, pipe 1, 3, and so on. All right? Let me set up the table that we're going to start doing our calculations on. I'm going to do it over here because we're going to need lots of space. And I'm going to have a column where I keep track of the iteration we're on. I'll have a column where I define which loop we're working on. I'll put the pipe name, the n value, R, Q, and then R times Q times the absolute value of Q, N times R times the absolute value of Q, and then delta Q and a corrected Q. So we've already decided that n is 2. There's 2 loops. So we're going to do, in our first iteration, we're going to do some stuff that's related to loop number 1 and some stuff that's related to loop number 2. The pipes that we're going to keep track of, inside of loop 1, there's pipe 1, 4, there's pipe 1, 3, and pipe 3, 4. And there's also pipe 1, 2, 2, 3, and 1, 3. For now, I'd suggest that you try and attempt this on paper. We will have plenty of time to translate it into Excel. But for now, try and follow the process of what's happening either on the board or copying it down on paper. N is going to be 2 for all of these. Okay, the R values for the pipes given on the problem, it's going to be 6, 3, 5, 1, 2, 3. So those are just taken off of the drawing itself. Now the hard part sometimes is just this step where we assign a guess flow rate. Okay, so here's what I'm going to guess. I'm going to guess that this 100 that comes in goes equally 50 here and 50 there. It's an okay guess. I could have done a little bit better. Maybe I should have put more flow through this pipe because it had the lower R value. Maybe I should have said 55 and 45. But that's okay. Eventually, the method itself will sort everything out and it'll converge on the right answer, as long as I satisfy continuity at each of the junctions. Okay, so I do have continuity satisfied at junction 4 because there's 100 in and 100 out. Okay, the next thing I have to do is have continuity satisfied at junction 2. And so there's 50 going out there. What I'll say is that 50 comes from 25 here. Let's see. Let me make this pipe 2, 3. I'm going to assume 35. And then that will mean that I have to have 15 coming here. And so at junction 3, there's 50 going in, and right now 65 going out. So I'm going to have 15 going that way to be able to get it to match up. And so now does everything balance? 50 going in to junction 1, and how much is going out? 20 plus 15, and 15 is 30, so there's 50 going out and 50 coming in. So right now, all of the flows balance. Now, there's nothing magical about the particular numbers that I picked. I could have picked other ones, but the important thing is that continuity has to be satisfied at each junction. Okay, so I'll put the flow rates in that I've guessed. I've got 50, 15, and negative 50, 15, negative 35, and then I'll put in this pipe a little bit later. So the values being positive and negative. So 50 is positive because it was, for pipe 1-4, it was up, which is clockwise. Pipe 1-3, if you look at pipe 1-3, from the perspective of loop 1, when I'm inside of loop 1, this flow being 15 down, that is clockwise, which is positive. So that's why I've got positive 15. And then pipe 3-4 is against clockwise. I'm just going to go through and work loop 1 right now. So for loop 1, the first thing I have to do is calculate R times Q times absolute value of Q. So R times Q times the absolute value of Q. That's 15,000 for this line. R times Q times absolute value of Q, 675. The same thing for this line is going to give me negative 12,500. And now I think you'll see why that absolute value of Q is there, is you don't want to have Q squared, because that would, you'd lose your negative sign if you squared Q. But because we have Q times the absolute value of Q, that allows you to preserve the negative sign associated with that being against the clockwise direction that was assumed. Now, let's add up these three things. If you add everything up, then you're going to have 3175. And we'll do the same thing, N times R times the absolute value of Q for this column. We've got 600, because it's going to be N times R times the absolute value of Q. So 600, 90, and 500. And so adding it up is 1190. That's the sum of these three values. So the delta Q that it's speaking of is going to be negative times the sum of R times Q, absolute value of Q, divided by the sum of N times R times absolute value of Q. So here, delta Q is going to be the negative of the sum of that divided by that. So negative 2.668. That's the delta Q for each one of them. And so the corrected Q will just be our guess of 50 plus the correction factor. So 47.332, 12.332, and negative 52.668. Yeah?
Why was it in 2 again? Is this 2 loops?
No, because we're using the Darcy-Weisbach equation. N is depending on what friction loss formula you use.
All right, gotcha. And what did you do to get corrected Q?
You take your initial guess Q and you add this delta Q. Other questions? All right, so we can do the same thing in loop 2, but there's a wrinkle, and that is what to do about pipe 1-3. You'll notice that pipe 1-3 is in both of the loops. It's in loop 1 and it's in loop 2. But when it's in loop 1, it was this initial flow direction, what we guessed, is positive because it's in the same direction as clockwise for loop 1. But now when we're working in loop 2, that's a negative direction. And so that's one thing that is probably the most common mistake people make when they're working these problems, is that you need to have the negative sign for the common pipes between loops have an opposite flow direction when you're switching from one perspective to the other. So where it was 15 positive for the first one, I'd want to say negative 15 here. Except that I have a better guess already for what the flow through pipe 1-3 is. Over here in this iteration, I said, well, actually, if you correct for things, it's not 15, it's 12.332. So I'm going to take this better guess that I have for that pipe, and I'm going to put it down into here. And so instead of negative 15, I'm going to say negative 12.332. All right?
What if you had just gone ahead and put 15 in and ran it? You still get the same answer eventually?
No, it won't. It won't converge if you don't do that step. It won't converge if you don't make it negative when it should be negative, and it also won't converge if you don't use the most recent guess of what the flow rate is. Okay, so we can go through and do the same thing as before. Calculate each of these parameters. Negative 12. Here, you mean? 15? In this loop? No. We're going to get a different delta Q this time. Okay, so R times Q times the absolute value of Q gives us 225. Then here it'll be negative 2450, negative 456.23. Add it all up, and it is negative 2681.2. All right, so N times R times the absolute value of Q, we'll have 30, 140, and 73.99. And so if we add everything up, then we get 244.0. We round. All right, so then the negative of that divided by that, which is what the delta Q is. Remember the formula for delta Q is on the screen over there. So the delta Q that we're going to apply, the negative of this divided by that, it's going to be 10.989. And so to find the corrected Q, it's your initial guess plus this delta Q. So that will make it 25.989, negative 24.011, and negative 1.343. The way you know you're done is when the delta Q's go away. When you keep doing this over and over again and there's no change from iteration to iteration, the solution is converged. In this example, the R's are given. It's kind of like how in the last homework assignment on the second problem the F value was given. You know, even though we know the F value depends on the flow velocity, we assumed some fixed F value. Well, in this example, I'm just trying to show you the structure of how the process works. When we do this for real, we're not going to work with R's anymore. We're going to use the actual F value, and the F value won't be fixed. But another indication that you're done and you don't have to keep converging is that the F values aren't changing either. So when the F values are converged and there's no more delta Q from iteration to iteration, then your solution is good. And it should still satisfy continuity at every junction. All right. You'll get the same flow rate for that common pipe. Yeah. That's right. One will be negative and one will be positive. Exactly. Well, let's just take a look at what iteration 2 is going to look like. So in iteration 2, loop 1, we've got pipe 1, 4, 1, 3, and 3, 4. The ends will still be 2. The R's will be the same, 6, 3, 5. Now, for the flow rates, this is a really important thing, selecting the right flow rate. What flow rate should we say for pipe 1, 3? Pipe 1, 4. I need to use the most recent version of that flow. And so I'll use 47.332. That's the most recent guess for that pipe. Okay, so the flow rate I'm going to use is 47.332. And pipe 1, 3, I'm going to go over here. This is the most recent guess, but I need to flip the negative sign. Because when I'm working in pipe 1, 4, I have a different sign convention than working in loop 2 than in loop 1. So what I put here is going to be 1.343. And then for pipe 3, 4, I'll just use this negative 52.668. 52.668. And then I can go through the same thing over and over. So you've now seen all like the mechanics, the structure of what you need to do to make this work. And now I think we're ready to try translating that into a spreadsheet and automating the process a little bit. So start Excel. Now remember that the example you see today is simpler than the example I'm going to give you on Tuesday. So the columns that we set up today are a little bit different than the columns we're going to set up on Tuesday, because this is sort of like the training wheels version of the Hardy-Cross procedure, where we're not really considering how F changes. On Tuesday, we're going to take the gloves off, and F's going to change right along with the flow rates. When you get the homework for the Hardy-Cross procedure, it's going to be full-fledged. Yeah, what do you said the doodle method?
Whatever, I don't know what you call it, but
You'll use the you'll use the nodal method on the homework that's due on Tuesday. What we're doing today, I haven't given you the homework assignment for that. Yeah.
are you gonna be here Monday for questions?
I think so. Yeah. Okay, so we'll just put our column titles in there. Iteration, loop, pipe, N, R, Q. R times Q times the absolute value of Q. If you want to get those lines, it's above the enter key. To get those vertical lines, shift, and then it's the key above the enter key. N times R times the absolute value of Q. Delta Q, and then corrected Q. Okay, so we'll start with iteration 1, loop 1, and just to make it easier, let me see. Let me paste the drawing of it on screen so that we keep remembering which pipe is which. Computer's locked up. It'll settle down. We'll use that. Come on. Okay, so we've got, got those columns. The pipes are pipe 1, 4. Oh, we got to do pipe. If we want it to say 1, 4, I've got to put in the quotation mark thing. 1, 4. Yeah. Pipe 1, 3. Yeah, it's thinking maybe you mean a date if you do it otherwise. 3, 4. But that little single quotation mark will allow it to remain as text. R values 1, 2, and 3. Okay, is everybody feeling good so far? Any questions? Okay, so the cues that we put in initially are, we could do a flow balance. There's nothing magical about these ones that I did. We'll go with it for now so that we can check against what's on the board. But later on, we'll adjust the flow rates to something crazy like 1 and 99. And it'll still converge eventually as long as you honor the continuity equation. Well, let's stick with a more reasonable guess. So we said it was going to be 50 through this pipe, 15 here, negative 50, so that the R times Q times absolute value Q, so it's equals R times Q times ABS means absolute value of Q, F14. All right, and I can drag that down. And for the next one, it'll be N, so equals N times R times absolute value of Q. So far, the numbers are matching with what's on the board. want to put in another space here. Okay, so now I want the sum. So equals sum of this range. And I can just drag that over, and it'll do the same thing on the next column. I'll put it in italics to remind me that that's something special, that it's a sum rather than calculated by cells to the left of it. Here's another important thing is that we're going to be putting the delta Q formula in. So let's copy that over. Here's the delta Q formula that we're going to be typing in. You have to type it 3 times. You can't just type it once and then anchor and drag. Things won't work out. You have to type the equation 3 times. So equals negative this divided by that. Equals negative that divided by that. It seems silly typing it in 3 times, but you have to, because of the way we're going to be copying and pasting as we iterate. Okay? And then corrected Q is simply our guess flow rate plus the change, so plus the delta Q. Let me expand that. Okay, so the numbers match up with what's on the board so far. Any questions? We can take a pause here. The battery die on that? Nice. The delta Q is the negative of that divided by that. Gil, how are you doing? Okay, so you do equals R, so just click there in the cell that's by it. Times Q, so then click there, times, I type in ABS on the screen, and parentheses, and click, not the close parentheses though. So now click in that cell one last time, and now close parentheses and enter. There you go. So you can drag that down for the other ones. That's right. Remember to do negative. Equals negative that divided by that. So you need to change the formulas up above too. Good. Taylor, how are you doing? Good. Oh, I'm recording this as I walk around the room. So we now can do loop 2. So the Q here, I'm going to use my initial guess was 15 for that because I don't have any improved guess of what the flow rate is through pipe 1, 2 at this point. Negative 35. But then here for 1, 3, I need to have this updated value. So rather than typing in the number, I'm just simply going to say equals negative and then click on that reference so that it reads in the updated magnitude of the flow rate and changes the sign. And then I can just highlight all of these cells and do Control C, Control V. And it applies the same calculations but to the next set of rows. So that's pretty nice. It saves me from typing in some formulas there. Okay, delta Q though, I have to type that in manually. So equals negative this divided by that. Equals negative this divided by that. And so on. Okay. When you have a spreadsheet you're going to give to somebody, and by default I think this had this many digits just because that's how much space there is, that's visually distracting. So scale it down a little bit so you're not showing all that unnecessary precision. Okay, the corrected Q will be the initial guess plus this correction factor. I can drag that down. All right. So that is the end of iteration 1. We're not nearly close to converged yet, though. Our correction factor, this delta Q, is still pretty big. So we need to iterate a few more times. So this is where it gets exciting. So we're going to have iteration 2. I'm just going to copy everything. I'll have to make some adjustments, but just to start off, I'm going to copy everything. So Control C and Control V. Okay, so what are the adjustments that I need to make? Well, here where it started with the flow rate for pipe 1.4, I'm going to have it say equals and then go up to this guess value here. Okay? Pipe 1.3 needs to be adjusted. Where's my best guess for pipe 1.3's flow rate? It's not up here. It's now this one. So equals negative of that value. And then instead of the negative 50, which was our initial guess for pipe 3.4, I'm going to say equals here, because that's my best guess for 3.4. Now look at the delta Q. The delta Q is much smaller in this second iteration than it was in the first, and that's an indication that things are as they should be. Your delta Q is getting smaller as the solution begins to converge. So I'll make some adjustments here. So for iteration 2, I want it to be my best guess for pipe 1.2, my guess for pipe 2.3, and then what do I do here? What cell should I have it refer to for pipe 1.3? Negative of this one. Very good. Yeah, I want to go within that same iteration. So equals negative right over here. All right, so the delta Q was 10 or 11. It goes down to 3. Things are converging. Now I can copy and paste a bunch of times and I don't have to make any changes along the way. So I'm going to zoom out a little bit. I'm going to highlight all of this. Now I've got to get the spacing right. Control C. Okay, boom. Look, the delta Q is getting tiny, absolutely tiny. I can do it again. Let's see, I want to paste it here. And the delta Q's are down to basically 0. And what's another indication that the flow rates are as they should be is look at the common pipe. Where? Where did it say error? Pipe 1.3? Pipe 1.3 is good. Well, like this green cell here? Oh, it's noticing that something's different compared to adjacent cells. That green thing is like a warning. Well, the formula in here is a little different from the formulas in other places, and that's the way it should be, because in the other ones I'm looking up there, but in this one I'm looking at here. It's just a warning that the formula is different than those cells that are adjacent to it. So the only thing I need to change is this was iteration 2, this was iteration 3, and this was iteration 4. But I didn't really even need iteration 4. Things have stabilized nicely before I even get there. So that's to 3 digits. Let's make this to 3 digits. All right. Pretty brilliant, right? That's the same process that can be used in structural applications, but here it was used to really what it's doing is it's making sure that regardless of path taken through the network, you have the same amount of energy at every location regardless of path. So at 4, you should be able to go through this pipe or some other path and get the same amount of head at 1. This is an energy balancing method. It's accounting for the energy in the system so that regardless of the path you take from one point to another, you get the same amount of energy at the destination. Any questions about this process? Okay, the recording of this, the screen capture recording, I'm going to post this afternoon. So if you need to go through the spreadsheet a little bit more slowly and figure out what cell came from where, it'll be there and you can go through it as many times as you like. I'll also be in the office much of the day tomorrow and much of the day on Monday. So you know, you don't have a homework problem yet where you need to apply the Hardy-Cross method. You're still working on the nodal method for the assignment that's due on Tuesday. So we've still got some more time for Hardy-Cross to digest before you need to start working on the assignments. But that is it for today. Let's take one last look at the announcements here. Homework's due on Tuesday. Those two problems.